My name is Joy Perez.
My name is Brian Nava.
For this presentation, the research paper for our group was on water copper nanofluid used in an open loop pulsating heat pipe. The objective of this experiment was to improve the thermal performance of the heat pipe by using a water copper nanofluid as the working fluid in an open loop pulsating heat pipe. For some background, nanofluid consists of solid nanoparticles in the fluid, which could enhance the thermal performance of the working fluid. Previous research on nanofluid used in heat pipes has had varied results, including one study with gold nanoparticles used within a loop heat pipe, which resulted in no major improvement to performance. Another study showed that nanoparticles caused obstructions to the heat pipe, resulting in a higher pressure drop across the wick. For this experiment, the following parameters were implemented. Two working fluids were used to compare the results. The first fluid used was deionized water. The second fluid was the water copper nanofluid, which consisted of 6 grams of deionized water with a 5% per mass of copper nanoparticles, with a diameter of 29 nanometers. The heat pipe used was an open loop pulsating heat pipe using copper tubing with an inner diameter of 1.5 millimeters with a total length of 4 meters. 20 type T thermocouples were also used to monitor temperatures throughout the heat pipe. A heater was also attached to the evaporation section, as well as a fan blowing air across the condensation section at 2.5 meters per second. The ambient temperature was kept at 18 to 20 degrees Celsius. The experiment tested the heat pipe in 3 orientations: horizontal, the evaporator above the condenser, and the evaporator below the condenser. So for the experimental results in the horizontal orientation for the deionized water, there were no significant pulsations. However, for the water copper nanofluid, pulsations began to appear at 40 watts and are more apparent at 50 watts, with amplitudes around 5 degrees Celsius at the evaporator, 22 degrees Celsius at the adiabatic section, 23 degrees Celsius at the condenser, which was caused by the lower fluid velocities at 40 watts in comparison to 50 watts. When comparing the average temperature of the fluids in the evaporation section, the water copper nanofluid has a mean temperature of 90 degrees Celsius, while the pure water has a mean temp of 118 degrees Celsius. An improved thermal performance would be expected for the water copper nanofluid given the lower evaporation temperature. The results for the evaporator above the condenser show similar results in the horizontal orientation. In the evaporator section at 40 to 50 watts, the water copper nanofluid shows a lower mean temperature, while the pure water shows a greater mean temperature.
For the evaporator below the condenser, we got the same behavior I was presented as the previous graphs with the different setups. Well, we got the nanofluid with the copper to have a lower mean evaporation temperature compared to the pure water. Some factors that we believe that could be related to this decrease in temperature is nucleation sites. More were created, which created more bubble generation and displacement. With the more displacement of the bubbles, we have more liquid to be pumped throughout the tube, which keeps the evaporation section temperature lower for the nano. But also, we believe the bubble critical diameter played a role as well, where we have the nano to be smaller compared to the water particles. Since the nano had a smaller diameter, we believe it increased the vapor bubble formation, which increased more intensified pulsations for the heat pipe. Based on the results, we got a thermal conductivity graph. Based on this graph, we were able to see, even though the nano had a higher conductivity compared to the water with the lower temperature, We believe due to nucleation sites, more solids were thrown into the mix of the fluid and the bubble generation intensified, especially in the high heat loads. Based on these loads, it created a lower thermal conductivity for the vapor than the liquid. Since there is a lower conductivity, there is more vapor presented for the pulsations. With the more pulsations, give us a 15% increase in thermal conductivity compared to the water. And based on performance ratio, we got at low heat loads for the nanofluids, the temperature difference for the adiabatic and evaporation were smaller for the higher heat load sections. From this, we could say in the lower heat loads, we could say film evaporation effects were more predominant than nucleation boiling. We believe since the increase of the copper nano, we had the increase of the thermal conductivity, which had a direct affiliation with the film, and with this film affected the pulsation flow. But as heat increased, we noticed that nucleation boiling takes over once the heat is increased. So based on this, we could say the open loop pulsation heat pipe for the nanofluid had an improved thermal performance effect. We got a greater amplitude with the nanofluids, which created more nucleation sites, which had more bubbles formed, and which gave us larger intense pulsations. So the more pulsations, we had more vapor presence, which gave us more thermal conductivity. And also, based on the performance ratio for the copper nanoparticles, we saw at low heat loads, the film evaporation was more dominant based on the increase on thermal conductivity of water. And for the higher heat loads, which when the heat increased, the nucleation boiling took over the pulsation flow. So after research, future improvements could be found in the studies to better understand how the nanofluid influenced to the overall operation characteristics of the heat pipe. But also, more investigations needed for the surface tension and shear stress effects, since they were very expensive in order to maintain. But since these investigations are needed because it gives us poor operation ability, but also more quantitative data on real-time applications are needed since more companies and engineers are looking to install it in electronics for the cooling, but also heat pipes so far are only in the mini diameter range, which means it's very difficult to create these. So the next step is to see how small can the heat pipe be, but also still be thermally useful device. And based on previous lectures in class, we found out once the heat pipe is dried out in the part, that means the heat pipe is no longer in use. So dry out mechanisms remain still unexplored, which would help a lot. But also the first principles still remain quite elusive, and more understanding is needed to create a comprehensive scheme for the mathematical model of the heat pipe.